Okay, what I want to get into today is what's known as the inverse square law. And basically it's why that force of gravity equation decreases with the distance squared instead of just decreasing with the distance. Alright, so why doesn't, if you triple the distance between two objects, why doesn't the force of gravity decrease by 3 instead of decreasing by 3 squared, or 9? Okay, well, let's look at some other things that follow the square law. Let's say we've got a pizza, and we've got one that's 1 meter in radius, and we want to look at one that's 2 meters in radius. Do I get twice as much pizza? Okay. No, I get 4 times as much pizza because the area of the pizza increases with the pi times the radius squared. Or in other words, I've got one there, I've got another pizza here, and I've got another pizza here. So that's how I can fit 4 pizzas in 4 1 meter pizzas in a 2 meter radius pizza. That obviously would be a big pizza, but just go with it. Okay. So if we look at light, also obeys the inverse square law. Light gets dimmer with the distance squared. Okay. Why would that happen? Well, when a light shines, light shines out as a sphere. Okay, and the further away you get from that light, the bigger the radius of the sphere, and the dimmer that light appears. Okay, so if we picture a hollow sphere, and we want to look at the light that's impinging upon the inside wall of this. I know it only looks like a circle, but that's because it's easier to do two-dimensional things on PowerPoint. Now, if I were to double the radius of that sphere, so go from here to here, okay, now that light would be spread out over a sphere wall, which is 4 times as big, because the area of a sphere is 4 pi r squared. So that light is spread out over 4 times the area, and therefore it's going to be 4 times as dim on the walls. Okay, so similar to the pizzas. Okay. The book, an old version of the book, like this butter gun idea, and this butter gun obeys the inverse square law. So when it sprays out its butter, if you put a piece of toast that's 1 meter away, you get 1 inch thick of butter. Oh, that's a lot of butter. Okay. If you put the toast 2 meters away, well, you can fit 4 toasts on the spray pattern. So that spray will spread the butter out over 4 pieces of toast. Now it's only a 1/4 inch thick. That's better. Okay. And if you put that spray pattern, if you go to 3 meters away, now we can fit 9 pieces of toast in the spray pattern, and now the butter will be 1/9 as thick. So the butter is getting dimmer? No, I don't think so. So anyway, there's a lot of things that follow this inverse square law, getting smaller with the distance squared. We've talked about gravity, we've talked about light. Sound obeys the inverse square law. Sounds get softer with the distance squared. Magnets get weaker with the distance squared. And radioactivity gets weaker with the distance squared as well. So a lot of things follow this. So if we were to look at a graph of the gravitational strength as we got away from the surface of the Earth. So here's a picture. We've got this amount of force if we're 1 Earth radius away. Okay, an apple, let's say, weighs 1 Newton, so this force is 1 Newton here. Okay. If we go 1 Earth radius above the surface, we're 2 Earth radii away. Okay, that apple now weighs 1/4 of a Newton. Okay, and if we're 3 Earth radii away from the center, now the apple weighs 1/9. And how much is the apple going to weigh here? 4 Earth radii away, 1/16. Okay, all right. So on to some other things related. So let's say, what happens to your weight as you climb a mountain? Well, you get further away from the surface of the Earth, or from the center of the Earth, and therefore your gravity gets weaker on you and you're going to weigh less. Okay? So let's say you're halfway up a mountain, and then you reach the very top, and you're twice as far away from the surface of the Earth. Okay? Is gravity 1/4 as weak on you here because you're twice as far away from the surface of the Earth. Okay? No. Okay? It's not. Well, first off, this is a pretty extremely exaggerated mountain. There are no mountains that stick out quite that high. But even if we did have a mountain that was that tall, you would be in outer space at the top. So you still wouldn't be 1/4 your weight at the surface at the top, okay? Because you're not twice as far from the center. Okay, it's really how far you are away from the center that matters. Okay, the distance didn't double; it increased by 10% or something like that. Okay. How far away from the surface would you need to be to have your weight reduced to 1/4 of it at the surface? Would you need to be 1 Earth radius away or 2 Earth radii away? Well, remember, in order to have your weight cut in 1/4, you have to double your distance. Okay, you're at 1 Earth radius already, okay, and therefore you would just need to be 1 Earth radius away from the surface. And now you're twice as far, okay, and therefore your weight is 1/4. All right. Now your weight, which is just a special case of gravitational force. Okay, it's the force of gravity on you by the Earth. Okay, there's an infinite number of gravitational forces that are going on in the universe. This just happens to be one special case that's pretty important to us. Okay. But so when the Earth attracts you, okay, and let's say you weigh 150 pounds, okay, you attract the Earth, okay, which is stronger, the force of gravity on you by the Earth, okay, the Earth pulling you or you pulling the Earth, who pulls harder, you or the Earth, okay? Well, it is the same. Remember Newton's third law, okay? The force of gravity on you by the Earth is the same as the force of gravity on the Earth by you. All right, so it's the same. And so you attract everything in the universe that has mass, not just the Earth, but the sun and the moon and distant planets and distant stars and gas pockets and whatever. Okay, so this is kind of interesting to think about, that you're pulling on them. And of course, they're not going to all come crashing down on you because they're moving and things like that, but some interesting things to think about. So the shuttle orbits the Earth at 200,000 meters above the surface. How strong is gravity here? Here we've got a picture of the shuttle. And here we've got pictures of astronauts floating in a spacecraft. Why these are such poor quality photos, I don't really know why, but they're the ones I found. Okay. Well, what I want you to think about is that the radius of the Earth is 6,380,000 meters, or 6,380 kilometers. So let's look at it in terms of kilometers. So 6,000 kilometers. Okay. You're at another 200 kilometers. So I tried to make this to scale. So you're basically this far, okay, away from the surface of the Earth. You're not really, that far away from the Earth, even if you are considered to be in outer space. And so when we want to look at how much gravity is going to get weaker, we look to see how much gravity has gotten weaker compared to the center of the Earth. So if this is your gravity at the center of the Earth, and then you go this far, and you're now this far from the center of the Earth, the force of gravity isn't going to change on you very much. Okay. These are astronauts in space. These are astronauts that are in a training plane, which just goes into a dive bomb, and they're not very far from the surface of the Earth at all. Okay. What's going on here? Well, gravity is still 94% as strong at the space shuttle or at orbit elevation as it is at the surface of the Earth. Okay, what's making these divers, these astronauts and trainers appear weightless? Okay, it's the fact that they're in free fall. Okay, this plane goes into a dive bomb and it's in free fall. Remember when we talked about cannons going in orbit? or cannonballs going in orbit. So they're constantly falling towards the Earth, but they miss it because they're doing what? They're moving too fast, okay, to hit the Earth. So here we've got a picture of the astronaut in the spacewalk, and he is or she is moving really, really fast right now. Otherwise, if they were to come to a stop, they would plummet towards the Earth and hit, okay, if they were to stop moving, okay? All right. So why did all the planets turn out pretty round? Why don't we have any square planets? Things like that. Well, planets and stars and suns and all that stuff condense from clouds of dust, okay, interstellar dust. And if we were to look at a pocket or a square of space dust, and we were to look at the force acting on a little particle of this space dust. So here I've got a particle enlarged. Okay, every piece of space dust is pulling on every other piece of space dust. So if we look at this space dust right here, it's getting pulled to the right by these space dust pieces, and it's getting pulled to the left by these, and it's getting pulled down by this. Okay, well, the left and the right forces cancel, so it just goes down. Okay, so it's going to start to collapse. Okay, if we look at a corner, here we've got this piece of space dust is being pulled to the right by these. Okay, it's being pulled down by these. Okay, and it's getting pulled to the center by these. Okay, and all in between. Okay, these two forces aren't going to cancel fully. They're going to partially cancel, but the net result is it's going to get pulled inward. Okay, so the corners get pulled in and the sides get pulled down. So it all gets pulled together and it collapses into a fairly round object. Okay, and so all these gravitational interactions are going on. So when we have the planets that are moving around in their mostly circular orbits, the planets that is, they actually tug on each other. So when the sun, or I'm sorry, when the Earth comes by Mars, it actually pulls it slightly out of its quote unquote normal orbit, and it changes its orbit. That's actually how they discovered, was it Neptune or Pluto? Because the planet, if we still call Pluto a planet, was messing with the orbit of another planet. And here that is. So the furthest planet, Pluto, was discovered because it was causing Uranus to wobble a bit in its orbit. Okay. So kind of where I want to leave you with is the fact that Newton didn't discover gravity. What he discovered was that any objects pull on any other objects that have mass. Okay. And that this law of gravity that worked on Earth applied in the heavens. So the universe follows the same laws of physics as we are able to discover on Earth. So we're able to learn about the universe around us. Interesting stuff to think about. So here we've got two planets crashing. Maybe they'll coalesce into one galaxy due to their gravitational interactions. Who knows? But one thing is kind of concerning if you think about it. Everything in the universe attracts everything else in the universe. It's constantly being pulled. Okay, and what might happen if the universe was static and everything attracted each other? Static meaning it wasn't moving. Okay. It would collapse, okay, under its mutual attraction. Okay, it would collapse and smash into each other. Okay, so the universe was about about 15 is that billion years ago? Yeah, I think so. Started off as this small, condensed, amazingly condensed unit of matter, then it expanded. Okay, some people think, I don't know if this idea is as popular as it was, but some people might think that it would expand and it would slow down as it expands, kind of like throwing a ball up in the air. It would slow and then come to a stop. And then it might come back together and form what's titled the Big Crunch. So we got the Big Bang, the explosion in the beginning. Some people thought that the universe might be headed for a big crunch, but that's not what they seem to be finding out. Okay, what they're seeing is that the planets that are, or the parts of the universe that are further away seem to be speeding up. Okay. So rather than slowing down as it expands, it appears to be speeding up. This would be like throwing a ball in the air, and then rather than having it slow down and come back to you, it just took off like a rocket and sped up into the air. That would be pretty strange. So we got some interesting things going on. All right, almost done here. So let's say we've got, let's find the net force on this object using the parallelogram based on these two. And I do this because there's, on the worksheet, there's some similar ones. So we've got a force of gravity going to the center of that object. We've got a force of gravity to the center of this object. Remember making the parallelogram and then drawing the resultant. So we transfer this force here. We transfer this force here. We draw the parallelogram from start to finish. Okay, and this represents the force of gravity acting on this object, and it would go towards the center of these two objects. Okay, let's look at a slightly different scenario where we have a 1 kilogram and a 2 kilogram object. So now if this is 2 kilograms and we have this much force, how am I going to draw this arrow down like this to show that there's only a 1 kilogram object here? Well, the force is going to be half as much. Okay, so we finish off our parallelogram, so drag this down here. Okay, and drag this one up here. And our start to finish parallelogram, or resultant, goes from start to finish. And we'd be headed towards this point, pretty much. Okay, so what I want you to do is do a conceptual worksheets 12.1 and 13.2. Do not need to show work for 13.2. We're going to skip 13-1 for now. Enjoy your evenings.